Hi everyone, this is Huimin from University of Science and Technology of China. So now I'm gonna introduce you to our new work, Plug and Play Versatile Compressed Video Enhancement. So nowadays, the short video platforms are flower booming. Video has become one of the most popular multimedia formats, and due to the bandwidth constraint during transmission, after we capture and make the videos, before we distribute them, these videos are typically compressed with different compression levels, and therefore results in poor visual quality and suboptimal performance in downstream tasks. To address videos of different compression levels, existing methods typically adopt separate models to handle different inputs, which is inflexible, while the other methods consider such an ability as part of its generalization ability, but these are compression agnostic, and therefore they provide limited improvement. As a favorable solution, we would like the models to have the following attributes. First, it should adaptively enhance videos of different compression levels with a single model. And second, it should effectively assist various downstream tasks in a plug-and-play manner. And third, during the enhancement process, it should be efficient without causing a computation bottleneck. To this end, in this paper, we propose a codec-aware framework for versatile compressed video enhancement. This framework is able to enhance inputs of different compression levels while effectively assist in various downstream tasks. Our basic idea is to take advantage of the codec information embedded in the bit stream. So here let's take AVC as an example. In the bit stream encoded with AVC, there are some prior information that we can use. Specifically, AVC adopts a hierarchical quality adjustment mechanism. So for each video, you can adjust its quality by specifying the CRF or the CVPR value. And here we show the CRF value. For each frame, the codec automatically adjusts the compression levels based on the CRF value specified by the users. So here, the sequence-wise CRF and the frame-wise CRF construct the quality priors that we can use. And also, as we mentioned before, we want the enhancement algorithm to be efficient. Therefore, we further consider the partition map and motion vector embedded in the bit stream. The partition map allocates microblocks of different sizes for regions of different complexity. Therefore, it actually indicates the spatial complexity distribution of this current frame. The motion vector is similar to optical flow, while it models the temporal relationship in a blockwise manner, and therefore it serves as a cheap alternative for the flow. Together, the sequence-wise CRF, the frame-wise CRF, the partition map, and motion vector, they construct the prior information that we can leverage to effectively enhance the videos of different compression levels. Our proposed codec-aware enhancement framework has two subnetworks, CAA network and BAE network. They are responsible for the parameters estimation and frame enhancement respectively. In the CAA network, instead of equipping separate enhancement branches for different inputs, here we adopt the design of MOE, mixture of experts, to adaptively estimate model parameters for different videos of different compression levels, and correspond to the hierarchical quality adjustment mechanism in AVC. Here we also adopt a hierarchical adaptation mechanism to estimate the parameters. We have two stages here, the sequence adaptation and frame adaptation. In the sequence adaptation, we first construct parallel expert layers, which share the same architecture but has independent parameters. They serve as the basis of the parameter combination. The sequence-wise CRF is adopted as the condition to reweight the parameters of these expert layers. By doing so, the parameters of enhancement model is adaptive to the compression level of the input video sequence. In our implementation, we set the numbers of expert layers to 6, and as you can see that, each expert layer has a distinct preference for specific CRF values. Compared to the MOE that reweights output features, reweighting the expert layer parameters is computational efficient and comparable to the networks constructed by a single expert layer. That's to say our network is still efficient. For the frame adaptation, since each frame has quality fluctuation between the sequence and current frames, to flexibly enhance frames with different visual quality, we propose to reweight the sequence adaptive parameters using the frame-wise CRF. So together, the sequence adaptation and frame adaptation determine the parameters of the following BAE network, so that we can enhance videos of different compression levels through a single model, without changing the structure of models. In the BAE network, we aim to enhance current frame, and here the motion vector is adopted to align current frame and its reference frame, so that complementary information can be provided for the current frame. And besides, considering that different regions has different complexity, applying the same convolutional kernel to all regions is not reasonable. Therefore, in the region-aware refinement, based on the partition map, we extract the features with independent convolutional layers. Here we visualize the features in the region-aware refinement. As you can see, the output feature has more fine-grained and high-frequency details than the input features. And also, the refined features provide distinct activations for different regions. For example, the moving bus here and static trace here. So in the experiment, our evaluations are twofold. First, we would like to verify the quality enhancement performance on seen, unseen, and highly compressed scenarios. And second, we want to evaluate the versatility to assist in different downstream tasks on multiple compression settings. Our first and basic target is to enhance the input video. All of these inputs are enhanced with a single model. Compared with the classic methods such as MFQE and STDF, our methods demonstrate better performance and stronger generalization ability. Then we investigate the performance in assisting in downstream tasks. We select video super resolution, optical flow, video object segmentation as the downstream tasks. We first enhance the compressed videos with different methods and then feed them into the downstream models for corresponding tasks. So compared with the previous methods, pre-enhancing the inputs with our methods effectively improves the performance of video super resolution and reduce the compression artifacts here. On the task of optic flow estimation, we evaluate with a Kitty dataset. And you can see here, our method successfully corrects the mispredicted flow at the motion boundary of the moving car. Here we report the results of video object segmentation. The task of VOS is especially likely to give inaccurate result for the compressed input, since the compression blurs the boundary of object. And as you can see here, our methods successfully avoid such tendency. Finally, we also tried another generative task, video impending, which is likely to be affected by the compression artifacts due to the inaccurately predicted masks. Here are the results of the object removal, where enhancing with our methods provides minimum color distortion and remains the content. Okay, so previously we have demonstrated that our method is designed to be versatile. without any assumptions about downstream tasks, which ensure its broad application across various domains. And here, we show it can also be adapted to the specific applications when it required to be. We extend our framework to the task of video super resolution for the compressed videos. And by increasing the numbers of the basic blocks and incorporating a pixel shuffle layer at the end of the network, we convert the enhancement framework into a VSR-specific network. And as can be seen, although the proposed method is not tailored for the VSR task, it still provides competitive results with minimum computational complexity. This indicates the versatility and potential of our framework to serve as a general solution to leverage codec information in specific tasks. In the ablation studies, we start with a baseline that concatenates reference frames and current frame as the input without using any codec information. We then progressively equip the baseline with the motion vector alignment, the region-aware refinement, sequence adaptation, and frame adaptation to assess their contributions. As can be seen, incorporating the motion vector alignment and the region-aware refinement effectively improve the quantitative performance and provides results with coherent textures. For the adaptation part, by introducing the sequence adaptation and frame adaptation, we yield consistent performance improvement. Here we report the performance regarding different numbers of expert layers in the sequence adaptation. And as you can see, the performance is the best when set the numbers to 6. In addition, based on the temporal file shown here, incorporating frame adaptation helps to achieve a smoother temporal transition. In a conclusion, in this paper, we introduce a versatile codec-aware enhancement framework that adaptively handles diverse compression settings and serves as a plug-and-play enhancement module to boost various downstream tasks. Our method consists of a CAA and BAE network, which reuses off-the-shelf codec information to minimize additional computational cost. Compared with existing compressed video enhancement solutions, our method shows superiority in both enhancement performance and robustness, as well as the effectiveness in assisting different downstream tasks. And that's all. Thank you for watching this video.